In sections 6.6 and 6.7, we'll be looking at using the masses of the compounds and masses of individual elements to find what we call mass percent composition, or the mass percent. And that's just the ratio of the mass of the element within a compound to its total. This is important because very often you'll see percentages reported, such as if you look at a bottle of vitamins and it will say that it has a certain percentage of iron. It will say milligrams of iron as well, but it may say the percent of iron in the tablet. And that's usually mass percent. It's the mass of iron in the mass of the entire sample. So you would divide the mass of the tablet into the mass of the iron in that case. Now, when you divide the mass of the element by the mass of the sample, the entire sample, you get just the ratio. So we always multiply by 100 to turn it into a percent. Now, don't let the percent symbol here confuse you and think you're multiplying by 100 twice. The percent here is acting just as a unit. So we multiply by the number 100 to make it a percent. So if we look at an example of this, if we have, let's say, a sample of chromium, so that's an element, look on your periodic table, we have a 0.358 gram sample of chromium. And we're going to react that with oxygen. We're going to oxidize it to form the chromium oxide, and we end up with 0.523 grams of chromium oxide. So the difference between those would be the mass of oxygen that we take on. We would find the mass percent of the chromium by taking the mass of just the chromium, the 0.358 grams. Okay, and let's pick up our pen here. All right, so here's the mass of our chromium, the 0.358 grams, and then what's the mass of the entire chromium oxide that we created, 0.523 grams. Divide that out, we get the ratio of 0.685 something, something, something. We multiply by 100 to get a percent, and then rounding it to 3 sig figs, we find that we have 68.5%. Now notice when we're doing this, if we start with the mass in grams, we don't have to convert through to moles and then number of atoms or anything like that. It is a mass percent, so a mass ratio. If we've got mass to start with, we're good to go. We can plug that in. If we don't have the mass, then we may have to do some calculations to get to the mass. But as long as we've got those things, we're good to go. Now, the other nice thing about these mass percent compositions is that we can use them as conversion factors. We can convert between grams of some constituent element, so one of the elements within a compound, and the grams of the total compound. So, and vice versa. So, for example, we may be told that the mass percent composition of sodium within sodium chloride is 39%. So in other words, we want to know how much of just elemental sodium or sodium ions we would have in table salt. Okay, NaCl, that's just your table salt. Now that can be written as our conversion factor. It's a ratio of 39 grams of sodium to 100 grams of sodium chloride. So now if we have this ratio, we can use that as a conversion factor. So if we look at this, mass percent composition is 39%. Okay, that we know is mass ratio, so it's grams of sodium per grams of sodium chloride. That's what percent is telling us, as long as it's mass percent. So I can write that in my fractional form this way, 39 grams of sodium over 100 grams of sodium chloride, or I can reverse that. I can say 100 grams of sodium chloride in 39 grams of sodium, or per 39 grams of sodium. I can write it either way. Now I've got those conversion factors, and I can use those to get from one species to the other. Now, I told you can't get from one species to the other unless it's in terms of moles. Well, this isn't really switching from one species to the other. It's looking at a part of the whole. So it's like looking at the number of legs you have on the entire spider. All right, so let's look at an example of this. If we look at Food and Drug Administration recommendations for daily allowances of calories, vitamins, minerals, they put out recommendations for what adults should consume. And their recommendation is that adults consume less than 2,400 milligrams of sodium per day, which corresponds to 2.4 grams of sodium. So that's all well and good, but when we are consuming food, we're not consuming sodium ions. We're not consuming sodium metal, heaven forbid. We saw how reactive sodium metal was. I don't think you want to eat that. So the question is, if we can have 2,400 milligrams of sodium, what does that correspond to in terms of the sodium as we are consuming it, which is sodium chloride or table salt? How much table salt can we have and still be within these guidelines? All right, so what do we need to know to figure this out? Well, we know how much sodium we're dealing with. We want 2.4 grams or less. And remember, we said that sodium chloride is 39% sodium by mass percent, so grams over grams. So we're given two pieces of information. Now the way this is drawn here, it's a little bit confusing because it looks like they're adding numbers, and they're not. They're giving us two pieces of information. One is the fact that we start with 2.4 grams of sodium chloride. The other is our ratio, our conversion factor. 39% by mass of sodium, or 3.9 grams of sodium for every 100 grams of sodium chloride. It's just how much of the part do we have in the whole. And we are trying to find grams of sodium chloride. All right, so now on our solution map, again, you'll see, okay, I had told you earlier to get from grams to grams, you have to go through moles, switching from species. Well, there's an exception to every rule. The exception to this rule is when you're talking about mass percent. It wouldn't work if I were looking at this within some sort of chemical reaction. I was looking at the ratio of, for instance, water to carbon dioxide within a reaction. But here, again, I'm looking at how many legs do I have on one spider, that sort of thing. It's the grams of sodium within the sodium chloride over here. So those are related items, the sodium and the sodium chloride. So to solve, I would simply start with my 2.4 grams of sodium. I would set up my conversion factor so that grams of sodium cancel out. 2.4 times 100 divided by 39. I see that I'm only allowed 6.2 grams of salt per day. It may sound like a pretty good amount, but remember, a gram is the mass of about a single paper clip. So you're only supposed to have about 6 paper clips worth of salt a day. That's really not a lot of salt, especially when you consider that most of the prepackaged food that we have these days has salt added to it. Almost everything we buy commercially has some salt in it to make it taste better, even sweets. A lot of sweets have added salt to kind of offset the sweetness. So it's actually pretty difficult to stay within that recommendation of 6.2 grams. All right, so looking at another example. What if we look at a compound right here, chlorofluorocarbon? It has a carbon, 2 chlorines, and 2 fluorines. Okay, so the carbon is shown down here with the black circle, and then here are the 2 chlorines, the larger green circles, and here are the 2 fluorines with the smaller, lighter green circles. All right, now, if we want to know what's the mass percent of chlorine in that molecule, what we would need to know is what is the mass contribution from what I'm looking for, which is chlorine, okay, so right here, and then what's the mass contribution coming from the entire molecule. Now, to find the mass contributed by chlorine, first of all, I need to know what is its molar mass from the periodic table, how many grams per mole, and then how many of them do I have in the compound? Well, I have 2. So I have 2 times the molar mass. That will tell me how many grams of chlorine. Okay. And then on the bottom, I need to know the molar mass of this hydrocarbon. So I would need to add the mass of 1 carbon, 2 chlorines, and 2 fluorines, divide that out and multiply by 100. That would give me the mass percent of chlorine in this particular molecule. All right, now, if we look at this in action, they've changed the formula just a bit. Now, the previous one was a carbon with 2 chlorines and 2 fluorines. Here, they're using 2 chlorines, 2 carbons, 4 chlorines, and 2 fluorines. So this is also known as a chlorofluorocarbon, a CFC, that we talked about a little bit earlier in one of the previous sections. But this one in particular is known as Freon 114. Now there are several different kinds of Freon. There's a Freon 112, there's I think a 111. They're different formula numbers, but this one, 114, that we're looking at, we want to know the mass percent of chlorine in this particular molecule. So we've changed it just a little bit. All right, so what are we given? We're given a formula. Okay, we don't have anything else about it. We don't have a molar mass or anything, so we're going to have to do some calculating. We don't have our conversion factor yet. We'll work that out. We want to find the mass percent of chlorine in that original molecule. So here we start with the chemical formula, and we're going to work our way over to the mass percent. So we need the ratio. I need to, on top, figure out what mass is coming from just the chlorine. So I need the molar mass of chlorine. If I look it up on the periodic table, 35.45. And how many of them do I have? I go to my original formula, and I see right here that I had 4 chlorines, so that's where the 4 comes from. 4 times the 35.45. Okay, now on the bottom, molar mass of this, I've got to add those all up, and let's hop over to the next slide to see that a little bit neater than my writing here. Okay, all right, so here's the 4 times the 35.45 that we showed on the last page, and so that turned out to be 141.8 grams. Okay, so there's our chlorine mass. All right, now this next part is going to show us the calculation of the molar mass of the entire compound. So I see that I have 2 carbons, I have 4 chlorines, and I have 2 fluorines. So I have 2 carbons times the molar mass of carbon, which is 12.01. I have 4 chlorines times its molar mass of 35.45, and then I have 2 fluorines times the molar mass of 19. Okay, so the 12.01, 35.45, and 19 all come from the periodic table. You should have that out in front of you so that you can check these and look at them and be finding them as we go along. Do your math. 2 times the 12.01 is 24.02. 4 times the 35.45 is 141.8. And 2 times the 19 gives us 38. Add those 3 together, and we find that the mass of the entire compound, the molar mass, is 203.8 grams for every 1 mole. All right, so now I can plug my numbers in. So mass percent, I'm going to take the contribution coming from chlorine. That's going to go right here. I'm going to take the contribution coming from the entire compound and put it down here. Sorry, didn't mean to cover that up, 203.8. And then I divide those two, multiply by 100, and I find that the mass percent of chlorine in Freon 114 is 69.58%. Okay, that means there are 69.58 grams of chlorine in every 100 grams of Freon. So the majority of the mass of this compound is actually coming from the chlorine. Even though there's still 2 fluorines and 2 carbons, chlorine makes up the most of it, which makes sense. It's one of the heavier ones. It's heavier in terms of grams per mole, in terms of molar mass, than the other 2. And there's 4 of them, so it makes sense it would make a higher percentage. All right, and then just another little side note about chemistry and health. It mentions this in your book as well. So you may or may not, hopefully you are aware that municipal water sources are fluoridated. That means that they put fluoride. So remember, fluoride is the ion. So it's no different from fluorine other than it's not in its elemental state, it is in the ionic state. I'm sorry, that's supposed to be the letter F. So why do we put fluoride in our drinking water? Well, because it's been shown to strengthen tooth enamel. Strengthening your tooth enamel prevents tooth decay and cavities and abscesses and a lot of issues that people used to have with their teeth. People could die from, abscessed teeth and things that this day and age should not be an issue, but were big issues then. So people started putting fluoride in the water supply. But the question is, how much fluoride do you put in your water supply? Because if you put too much fluoride in your water, it causes a condition known as dental fluorosis, which causes these brown spots to appear on teeth. Not really harmful per se, but cosmetically very unattractive. And if you get the levels too high, it leads to something called skeletal fluorosis, which can be a health issue, which is a problem. So you don't want too much fluoride in your water, but if you don't put enough, then it doesn't create any benefits. Okay, so in order to see health benefits, adults need to get between 1 and 4 milligrams a day. Not very much, okay, but enough to help. So we want to get between 1 and 4 a day, but we don't want more because then we get those nasty little side effects. So the idea is to divide that 1 to 4 milligrams a day out throughout the water that people are drinking. And it was estimated that adults tend to drink between 1 and 2 liters of water a day. Okay, so if they're drinking 1 to 2 liters, then fluoride has been added to the water to create the beneficial effect of fluoride. So the question is, again, all we're interested in is fluoride, but it doesn't get added to the water as just fluoride. We don't have just ions floating around. Remember, you can't have any cation without an anion canceling that charge, and vice versa. So what we add to the water is sodium fluoride. So the question is, in order to get the level that we need, the 1 to 4 milligrams, and let's go for the lower level, the 1 milligram of fluoride, then what would need to be, first of all, what would be the mass percent composition of fluoride in sodium fluoride? Okay, so what's our mass percent? There's question number 1. And then question number 2 is, based on that mass percent and the fact that we need, again, let's go for the lower level, 1 milligram of fluoride per liter of water, okay, then let's say we have 1.5 liters of water, 1,500 liters, so we've got a large water supply here. How many grams of this sodium fluoride are we going to need in order to fluoridate that water to the level that we want? Okay, now this is a fairly intense, complex problem. The first one, number 1, okay, this is problem number 2 here. Problem number 1 is pretty straightforward. Okay, if we look at it, mass percent of the fluoride is going to be the mass being contributed from the fluoride. So we have 1 atom of fluoride in sodium fluoride, okay, times the molar mass, and I'm going to make you look that up, but the molar mass of the fluorine. Okay, now we're going to divide that by the molar mass of the sodium fluoride, and then multiply that by 100 to get a percent. All right, so I'm going to make you look those numbers up and do that, but once you have that number, you can then use that to solve number 2. And I'm not going to try to do it here, A, because I don't have space, B, because I seriously doubt you'd be able to read my handwriting by the end. This looks like a kindergartner learning to write. And C, or 3, whichever number system I was using there, number or letter, I want to use this when we come in on Friday for our recitation section. So I want you to have a crack at that. Remember, you had another challenge question earlier about how much money would everybody on Earth have if we had a mold of pennies and divided it amongst everybody on Earth. So a couple of challenge questions I want you to work on, see if you can come up with an answer, and we'll go over those on Friday along with plenty of other examples. All right, so that's your job. How many grams of sodium fluoride do we have to add to 1,500 liters of water to fluoridate it properly? All right, so that wraps up sections 6.6 and 6.7. We'll finish up sections 6.8 and 6.9 talking about some empirical and molecular formulas.